So, yes, I guess everything's ready. Okay. Yes. So, am I audible? Yeah, I guess. Yeah. Okay. Okay. So yeah.
Yes,
Yeah. Yes. Thank you.
sir.
Yeah. Thank you. Okay. So, welcome back again. So today, this is week 7 of the Introduction to Fluid Mechanics course, and again I'm sorry, like I was not able to take the session in the stipulated times because of some circumstances, and so I'm taking the session today. So yeah, since again only one student here today, so yeah, if you have any doubts regarding the concepts of week 7, I guess there are only two topics, mainly Euler's equation and the Bernoulli's equation. So yeah, you can ask right now. Meanwhile, also to just to understand whether you got the concept right or not, I will also ask some questions regarding that, so you may answer that. But if you have strictly some doubts, some particular doubts regarding these two concepts, you may ask. So yeah, Bernoulli's equation and Euler's equation. Yeah,
Hello, sir.
yeah, please go ahead.
Sir, regarding Bernoulli's equation.
Yeah,
Hello.
yeah, go ahead, please.
Sir, regarding Bernoulli's equation, I had a doubt. Actually, it's an assignment problem.
Okay,
Um, they had given some statements asking which one is not true.
okay.
So, Bernoulli's equation, like, is it valid only for steady state or is it valid for unsteady state also?
uh the thing is that the standard Bernoulli's equation that we know, that this one, p by rho g plus v square by 2g plus z is equal to constant. This one is only valid for steady state. And actually, if you may recall, this equation is actually derived from Euler's equation of motion, right? So after taking certain assumptions, actually there are four strict assumptions which I was going to ask, but still, after considering those four assumptions only, we reach to this final state of the equation, which is popularly known as the Bernoulli's equation, which basically is the conservation energy in viscous fluid flow. So yeah, so if in the question they have mentioned, strictly mentioned this equation, or in Bernoulli's equation in general, because this is the most popular form, and this is known as the Bernoulli's equation. So if they've asked like that, then it's only valid for steady state. There's no unsteadiness in the flow while considering the Bernoulli's equation. So yeah.
Okay, actually, equation was not mentioned. They had
Okay.
only mentioned Bernoulli's equation is not valid for steady state, something like that.
Yeah. Okay. See, the thing.
So,
Okay. Yeah. Please go ahead.
so I got confused, sir, because as you mentioned, this particular equation is for steady state.
Yeah.
That which one which you mentioned.
Yes.
But generally, it can be for both steady and unsteady, right?
Yeah. That is the thing I'm telling. It can be for unsteady, steady, and unsteady, and see. It might happen that the options that are given that might not be that you have mentioned. You have certain opinion that it is right, and the answer that is already being encrypted for this quiz may say that your answer is wrong. But the thing is, you should know the concept clearly. Okay, so this equation that I mentioned here, and as you might have gone through by the lectures of Professor Chakraborty, this form of equation, this Bernoulli's equation, is only valid for steady state. This is one of the important assumptions by deriving this equation. But if you mention in some case, like say in your exams, where subjective exams that you might have in your undergraduate or your colleges, if you write the unsteady form of the equation with that del v by del t term, then you can say that Bernoulli's equation is also valid for unsteady case, but this equation will take some different form, and it will not be this form. But if you are mentioning, you may write like, if you are mentioning only this form of equation, then it is valid for only steady state. And in general, I would say, in general, Bernoulli's when they are implying Bernoulli's equation, they directly imply this one. If they had mentioned unsteady Bernoulli equation, if they are considering unsteady Bernoulli's equation, they would strictly mention it. But if they are only considering Bernoulli's equation, then you may write for 90% of the time they are considering this equation, so you can say yes, it is only valid for steady state. But it might happen that they may assume something else, and in that case you should like strictly write yes, it's also valid for unsteady state, but the equation's form is not this one, but it takes some certain different form. You can mention like that. Okay.
Okay, sir. Thank you, sir. For concept wise, I had doubt. That's why I asked.
Okay, sure, no problem. Thank you.
Thank you, sir.
Thank you. Yeah. Yeah, so again, so welcome Abhishek and Anurag. So today we are discussing about the concepts taught in week 7 of the Introduction to Fluid Mechanics course. So uh, this week they have predominantly discussed about the Euler's equation and the Bernoulli's equation. So yeah, if you have any doubts regarding this concept, you may ask. Otherwise, like I will also to just to check whether your concepts are correct or not. I may ask some questions regarding these. So yeah, so now you can ask. So yeah, Abhishek and Anurag, you can ask. Okay, then I guess there are no doubts right now. So yeah, fine. So I guess if you have attended the lectures of week 7 by Professor Chakraborty, you might have encountered this form of the equation given by 1, say. So this is actually, I must say, an end product of a very long derivation from the Euler's equation of motion. So this equation is achieved after considering certain assumptions. Okay. If you ask me a number, I would say 4 strict assumptions they have considered to reach to this equation. So could any one of you kindly say some of those, like one by one, like there are 3 students, so each one can say one. So yeah, could you please tell me the certain assumptions that have taken to reach to this equation?
Hello, sir.
Yeah, please go ahead.
Uh, the important assumption was that the flow should be inviscid.
Okay, this is one of the assumptions. Thank you. Actually, this is what very precursor to the validity of Euler's equation of motion. So, in viscid flow is an important assumption or consideration to derive this equation. Okay, so Abhishek and Anurag, yeah, you can go ahead with the other 2 assumptions one by one. Like, please, I would request you to say, otherwise it would be monotonous. Yeah. Okay, I will wait for some time. If no, then I guess Priyanka can go ahead and tell the rest of the assumptions. So that's fine. Oh, okay then. No problem. Abhishek and Anurag is fine. So yeah, Priyanka, like if you know rest of the assumptions, could you please say? That's fine if you don't know, but if you know, please go ahead.
Sir, for the above case, the flow is steady
Okay.
and density is constant
Okay.
and it is taken along the streamline.
Okay. Okay. This is again a very interesting term or assumption that you have pointed out along a streamline. This is very only along a streamline. Okay. Good. So yeah, again, so everyone, if any general flow field is given and these 4 assumptions are valid in the given flow field, sorry, uh, these assumptions are this equation is if these assumptions are valid, then you can apply this form of equation only along 2 points that are situated along a streamline, the same streamline. Okay, along the same streamline. So it may not happen that if say the flow field has a streamline of these forms, say it's a very simple, say this is a streamline of a flow field, and yeah, I should point out like that also. Yeah, So if only these assumptions are given, then the Bernoulli's equation is only valid in points that are along the same streamline. Okay, so to be more accurate, say it is C1, C2, C3, this three streamlines. So this equation is only valid in points 1 and 2. This equation will not be valid between points 1 and 3. Okay, this is not valid because point 3 is at a different streamline. But again, if you would have attended lectures very properly, Professor Chakraborty would have mentioned clearly regarding a certain assumption or certain case where this equation would be valid in between any 2 points in the flow field. Could any one of you two, means since Priyanka has already spoken a lot, uh, so any one of two between Abhishek and Anurag, can you please tell me what was the special assumptions that made this equation valid for any 2 points in a flow field? Anurag and Abhishek, yeah, please. You may, if you're, yes, Anurag, please. It was Week-7. I'm really sorry, I couldn't get it. Could you please repeat, Anurag? Sir, I have not completed Week-7. Oh, sure, that's fine, Anurag, no problem. Thank you for clarifying. Okay, thank you. What about you, Abhishek? Like, you can. Same here. Oh, sure. Okay, no problem then. Thank you. Thank you. No problem. Thank you for attending at least. I hope I'm able to make your concepts clear. So yeah. Okay, you can mute yourself for now. Okay, thank you. So again, I'm sorry. So Priyanka, could you please go ahead and tell me that special assumption that we can take?
Sir, irrotational flow.
Irrotational flow. Okay, so okay. Say I don't know what irrotational means. So what I only know, I only know mathematics right now. So how do you express it mathematically? What is the mathematical formulation for irrotational flow, right?
So curl of the velocity vector is 0.
Okay, thank you. Yeah, absolutely correct. So if the curl of the velocity vector is 0, then the flow is irrotation. Okay, so okay, if I guess Abhishek and Anurag is new, so here I mentioned the arrow above the in general, in general field, I guess you mentioned do you not a vector like this. Okay, so in my case, since I have been in my college, they mention it like this, and one of my favorite professor used to mention vector like this, so I am mentioning vector like this. Okay, I put my arrow below the variable, so it's same. Okay, it's just same as this one, so don't get confused. Since you are new, I'm just pointing on rotation. Okay, so I guess it's fine. Yeah. Okay, yeah. So if, again, rightly pointed out, so if the flow is irrotational, then this equation 1 is valid between any 2 points in the flow field. Okay, again, the important thing to know is that, like, you cannot just say that if the flow is irrotational, then the Bernoulli's equation, sorry, then you can, I'm sorry, this assumption along with all the other three assumptions is needed to make this equation valid between any 2 points in a flow field. Okay, so yeah, I guess I was clear up to this point. Okay, yes, okay, thank you. So I guess Bernoulli's equation is clear. So again, I guess now I should have actually started with Euler's equation, but still it's fine. Only we can discuss Euler's equation as well. So yeah, so could any one of you please tell me the any form, like in Cartesian coordinate, I guess that is the most popular one, in Cartesian coordinate or in vector form also, what is the governing equation, what is the form of the Euler's equation? Could any one of you please tell me?
Sir,
Yeah, please go ahead.
some minus in Cartesian form,
Okay. Yeah.
minus dou p by dou x
Okay.
plus rho bx
Rho bx.
is equal to rho into ax.
Okay. Okay. So yeah, thank you. Yeah. So Anurag and Abhishek. Okay. Just out of curiosity, I would just ask one of you. Anyone who can. Any one of you can answer. Okay. So what term? Say if you know that Navier-Stokes equation is the equation that governs all the flow field on this earth. Okay, it's all the flow field. Actually, I'm wrong. All for all Newtonian fluids, Navier-Stokes equation, to be more precise, Navier-Stokes equation valid for the fluid for all Newtonian fluids. Okay, Newtonian fluids. So, given this idea, what do you think makes Euler's equation different from Navier-Stokes equation? Like, there's only one term missing specifically. So, could you point out that term?
So the viscous effect is missing here.
Oh, yeah, yeah, absolutely correct. So the viscous effect would be missing. So I guess we could write it as mu. Okay, in Cartesian coordinate. Yeah, I'm right, I guess. Yeah, I guess I'm not wrong. The viscous term would be denoted by this. If I'm wrong, just point me out, okay? Because these are very long questions, I may forget. So yeah, so rightly pointed out. This Euler's equation, again, just for comparison, I will write the Navier-Stokes as well. I will write in vector form. Okay, so it's very easy. It is concise and very easy to understand. So in for Navier-Stokes equation, in vector form, it will be written as, okay. Again, if I'm wrong, please correct me. Okay, plus v dot. Okay, and Euler's equation, like if you, since you got the concept right, only the minus Navier-Stokes minus the viscous term is the Euler's equation. Same. Oh, sorry. Okay. So yeah, again, since we again have to discuss the some questions regarding the week 7, so I would not go through the detailed derivation from the Euler's equation to the Bernoulli's equation. I suggest you watch the lectures of Professor Chakraborty, because he has very clearly and beautifully explained the concepts. Nobody could do better than him. So I suggest you watch the lectures. If you have any doubt, again, you can just approach to the discussion forum or just mail me. I will also share my email ID. That's fine. But uh, yeah, I would suggest you to look at the lectures. But again, just to out of curiosity, I may ask. Okay, I will ask. I will ask something. Anyone who can answer. Okay. So as I mentioned, that Navier-Stokes equation is valid for the flow of Newtonian fluids. All the Newtonian fluids, it is valid. Okay. And if you know, like, there are no such fluid which is in viscid. There is no fluid that is not viscous. Like, every flow field is viscous, and in that's why this equation in general is always valid. But still, here we are discussing our Euler's equation, which is actually a uh, physically not possible. If you look into it mathematically, you can frame the equation, but physically it's not possible for a fluid to be in viscid, right? But still we are studying it, and it's an integral part of any fluid mechanics course. You pick up any fluid mechanics book, you will see a course, a subject on sorry, a chapter on in viscid flow, dynamics of in viscid flow. You will definitely get the chapter. So could anyone who please tell me like why we are considering or reading these topics when they are physically it is not possible or physically not possible to have such flows? Why are emphasizing so much on these topics in viscid flow? Could you please tell me, any one of you? You can please go ahead. Like it is a very conceptual question, and you will in the later part of the question you will get to understand. But just out of curiosity or make all of you motivated regarding the course, regarding the rest of the course, I'm asking this question like why to read Euler's equation? Why to study in viscid flow?
Hello, sir. Just a guess.
Okay, sure, please.
Because it is very simple form of equation. That is why we study that basically.
Mm, actually, uh, you can, yeah, mathematically you're obviously correct because you do not have to deal with this term, obviously. It's understandable. But actually, the most annoying part of solving Neversov is this part of the equation, the advective term. This is the most annoying part. Like, if you know the differential equations, like, I don't think, I'm sorry if I'm wrong, that any one of you like are very fluent in solving nonlinear equations, that too second order. If I'm not wrong, please don't mind if I'm wrong, okay? I'm just saying as a general point of view. Even when PhD, I don't know like anyone who is really pursuing nonlinear equations. I'm trying to, but it's very difficult. This part is the most annoying one. So mathematically, if you're considering, I don't think removing this term in any way simplifies the equation. Yeah, it makes this equation a bit shorter in it, but doesn't simplify the equation at all. But you can say like it is fine. Yeah, it looks simpler, but it's not easy to solve. It's again difficult only. In most of the cases we consider steady flows or 1D flows to make the to avoid dealing with this term. So in some sense that is correct, but it is not the answer, right? So yeah, Abhishek and Anurag, just a wild guess like Priyanka, like could you tell why you are dealing with Euler's equation when it is not physically valid? Like physically there are no flows that are in viscid. Please, just a wild guess, that's fine.
Maybe the velocity is same all over the time
uh
on the right to go on the right.
okay, Anurag, actually, I didn't get the later part of your conversation. Could you please repeat? Yeah, please.
The velocity we can take along the line that's constant.
Mm, the thing is, what you have said is actually correct, but you have explained it in a wrong way. So that's the funny part. But conceptually, you are correct. Like, but you're explaining it in a wrong way. You're missing a very important part of it. But still, very good guess, very good try. Abhishek, what do you think? Please. Uh, you may write if you're in a very noisy environment. You may write it. But that's fine. You can write it. Okay, I will just start to just discuss a bit. Then we will directly go to the question and answers. But just as a motivation for all of you to study Euler's Euler's equation, why do we study it? And most of the times in interviews we encounter these questions. In fact, I was asked the same question. Okay, so Abhishek, are you writing in the chat or should I tell the answer? What do you think? Okay, I guess it's fine. Very good. You all of you have made very good guesses, and I'm really happy. So thank you. Okay. Say, have you any one of you and heard the term boundary layer? Boundary layer.
Where the viscous effects are felt.
Yes. Like, have you heard the term boundary layer?
Yes, sir.
And are you familiar with the concept of boundary layer? Just a vague understanding. It's fine.
Yes, sir. Just a vague understanding. The same thing which I said.
Okay.
where viscous effects are felt.
Yeah, you're correct. So yeah, uh, absolutely correct. So I will just give a bit more idea. So the study of Euler's equation, or the necessity to know the flow fields, or precisely the pattern, the way in which the flow would have behaved if the flow was inviscid. You get it right. I'm really clear, and if you are having doubt, please ask me to repeat. Okay. So the thing is, the way in which the flow would have behaved if the flow is inviscid, this thing, this concept, okay, I should write it, I guess. Okay, it is very helpful to know how the flow would have behaved if the flow was inviscid. Okay, this is very important. This is very helpful in many sense, and it is because of the effect of boundary layers. So yeah, so as rightly pointed out by Priyanka, so boundary layer is a region where the viscous effects predominate. Okay, viscous effects dominate, and uh, viscous effects drive the flow, you can say. So say, I'm sorry, actually I'm not conceptually correct. Viscous effects are dominant, you can keep it like that. So say this is a flow or a flat plate. Okay, there is some u infinity that approaches the flow, the free stream velocity of the flow denoted by u infinity, say, and after striking the flow it generates a boundary layer. Okay, let me use different color. Yeah, it generates a boundary layer. So you need to know that boundary layer is not a physical line or physical uh, what to say entity. Okay, it is just a imaginary line or surface. Okay, it's actually the point where the velocity u becomes 0.99 of u infinity. Okay, so you can draw the velocity profile like this. So the velocity profile would be, so yeah, this is uniform, but just after reaching the boundary layer, or okay, so the velocity at the surface would be 0. Why? Could anyone please tell? Because of no slip condition. Okay, thank you. Everyone said correctly, right? So because of no slip condition, the velocity at the plate surface would be 0, and because of the momentum transfer from the upper layers of the fluid that are traveling at a higher velocity, the velocity of the flow would increase, right? So it will increase up to, what is the maximum value that it can reach? What is the maximum velocity that it can reach?
The u infinity. Yeah.
So the maximum value that the velocity could reach after starting from 0 from the surface of the plate would be u infinity. But just, and obviously for very good reasons, we take a limit up to 99% of u infinity. Okay, so we say that the point at which the velocity reaches 0.99 of u infinity, that point we will consider as the boundary layer. So you can see after reaching this point the velocity becomes almost equal to infinity. Actually, if you draw it, this length should be equal to this length. Okay, actually that's why I increased the length to be mathematically or correct, because vectors length also plays a very, it's very important while denoting. So vectors same length have the same magnitude and same direction also, then the vectors are equal. So this length should be equal to this length, and you can see these vectors length slightly increases as we move ahead with the ahead of the as we move away from the plate. Yeah, so the understanding is that uh, with certain up to certain accuracy, like a very high accuracy, we can is assume that the flow within the boundary layer is viscous or highly viscous, and the flow beyond the boundary layer could be essentially considered as inviscid. Okay, is that clear? I will explain a
Yes,
bit
sir.
more. Yeah, up to this much is clear, right? Yeah. So, and see, the thing is, you need to understand again this concept. Okay, uh, many times you may get confused. See, it is not like that after reaching after crossing this layer, the flow suddenly becomes inviscid. See, it is not possible. The mu of the flow field can never be zero, right? Mu can never be zero. Mu would have certainly have some value, some positive value. Okay, and it also doesn't mean that after getting going inside this layer, the flow becomes highly viscous. Like it is, say in order of magnitude. If we say it is in order of 10, say it's a very vague understanding just to make you understand regarding the concept. Say the viscous effects are order of 10 here. You cannot say the viscous effect are absolutely 0 here or 0.00001. Say you cannot say it like that, or actually 0, you cannot say exactly 0. Okay, see, the thing is that you if you have for the in the very starting of the course, I guess I have mentioned the Newton's law of viscosity. So I guess it was given by tau is equal to mu del u by del y, right? Just for 1D flow, we are not considering the entire stress tensor. Okay, just for 1D flow, you told that tau was mu del u by del y. Okay, so in this case, it is the shear stresses are manifested by the presence of the velocity gradient. Am I right? Like, did you understand it? Okay, I will repeat. See, for this term to have some positive value, say like if this term is equal to 0, say if this term is equal to 0, say tau is equal to 0. Okay, and I'm emphasizing the fact that mu can never be equal to 0. Then under what condition that then can tau be equal to 0?
Dou u by dou y should be 0.
Yeah, so only when this is 0, tau can be 0, because mu is a property of the fluid. There is no meaning of mu equal to 0, right? It is not possible. So del u by del y equal to 0. So the concept of boundary layer is that, okay, again listen carefully. Okay, so uh, after crossing the boundary layer, the velocity gradients become so small that they cannot manifest the shear stresses because of the presence of the plate. Is that clear? Please say if you didn't understand. I will repeat it. Okay, sure.
Sentence.
Okay. Yeah. So what I mean to say is that within the boundary layer, you will have some certain value of del u by del y. And also mathematically, you can also see like there is a certain slope here, and this slope decreases up to a point when we reach here where this slope becomes 0. Okay, obviously you need to take into consideration the coordinate system. Like if you measure the slope from here, then this slope becomes infinity. Okay, so I'm considering from here, measuring it from here. Okay, so it is initially very high. Like if you rotate a bit, so if you're measuring from here, so say if you're measuring the slope from here, say this is theta, so this is very high, right? This is very high. Theta 1 is high. Then if you consider here, this is theta 2, this is theta 3. I can zoom it, I guess. Yeah, this is theta 3, and this is theta 4. So which is the highest, theta 1 or theta 4? Which is the highest? Yeah, theta 1
1.
is higher than theta 4. So theta 1 basically implies the slope. Like if you consider this as y and this as uh, u, and you're considering theta from this side, then the slope would be given by del u by del y. Say, I'm not saying this one, okay? I'm saying theta is that one. So be clear. Given this coordinate axis and measuring the angle from the y axis, uh, del u by del y basically, sorry, I have to zoom out here. Del u by del y basically gives the slope, right? So you can see here that when we reach the boundary layer, the slope becomes almost equal to 0, right? But it is not equal to 0. And in theory, like, you have to move very far away from the plate, okay? That's why it's 0.99, not exactly infinity. You have to move very far away from the plate to have the velocity gradients to be equal to 0, okay? So but we are saying for certain approximation, because if you continue to do take certain assumptions, say 0.999, then again more accurate it would be 0.9999. So you can go up to n order, that's fine. But for for engineering perspective and to save time, we say up to 0.99. We want the accuracy up to 0.99, okay? So keeping that in mind, you can see the slope almost becomes 0 at the boundary layer, right? So this basically means that when del u by del y is, when del u by del y is almost equal to 0, what do you think the shear stress would be? Shear stress, what would that be?
0.
Yeah, this will be almost equal to 0, right?
0.
Yeah, almost equal to 0. And what will be the shear stress here? Shear stress here. Very high, right? Very high. Am I right? Like, are you confused? Shear should be very, very high at the near the plate.
Yes, sir.
Yeah. So did you get it right? So the it is the combined effect of the viscosity and the velocity gradient that determines the shear stress. So viscosity exists, but the velocity gradients are not available after crossing the boundary layer, because of which they cannot manifest the presence of shear stress, because they cannot manifest the presence of shear stress because of the presence of the flat plate. Is the statement right? Is it? Did you get the statement? Okay, I will repeat it. Okay, again clearly. See, after crossing the boundary layer, the velocity gradients are so small. Velocity gradients basically means del u by del y term. These are so small that they cannot manifest them. They cannot manifest the shear stresses generated because of the presence of the flat plate in the flow field. Okay, I guess it's clear. It's clear, right? Yes, no.
Yes, sir.
Okay,
Yes, sir. Yes, sir.
okay, thank you. So yeah, so you again have been thinking like, why are discussing boundary layer? We have not reached the point why to discuss Euler's equation. So any guess now after reaching this again? Okay, one more knowledge. The order of magnitude of this boundary layer is very small. Okay, say if the plate is 1 meter in length, I would say the boundary layer would be, okay, let me calculate. It would be the order of millimeter, okay? 1 millimeter, it will be the order of 1 millimeter. Say if I denote it by del, then del is the order of 1 millimeter. If the plate is 1 meter in length, say, and this is again I'm a vague understanding, okay? After solving boundary equations, like I'm just recalling the answers. So, but it is of the order of 1 millimeter. So now could you improvise your answers, like why to study in viscid flow, even if the flow is predominantly viscous all the time, or not predominantly, it's actually viscous all the time, but still we need to study Euler's equation or in viscid flow. Now could you improvise your answers why to study in Euler's equation?
Because outside the boundary layer, we can consider it as inviscid flow.
Yeah, absolutely. See, like if you draw draw to scale again, so just as a again a vague approximation. See, if this is the flat plate and this is the flow field, okay, flow field over the flat plate. So if you draw to scale, the boundary layer would be, okay, I should zoom in. The boundary layer is only this region. So you can see, I guess, understand where the viscous effects actually dominate, and the rest of the region is predominantly inviscid. This is viscous. So see again, uh, to know the if say again we reach to this statement, okay. So say if we knew the flow pattern above a flat plate or any geometry, keeping in the assumption that the flow was inviscid, then the similar flow pattern would have not exactly same, okay, the similar flow pattern would have been available for the most part of the flow field except this region. So again, okay, there are very mathematical connections, there are perturbation theory, I guess you read, okay, I guess you can see in this page. So there's perturbation analysis to relate or to match the solutions from the inviscid flow and the viscous regime, okay. But this is beyond the scope of this course, but just to give you an idea, because of the fact that predominantly in the very predominant part of the flow field is dominated by inviscid flow, okay. Flow is viscous but the velocity gradients are too small. Since the predominantly, okay, I should write it again. Here also mu is not equal to 0, but del u by del y is equal to 0, okay. It's important, okay. Velocity gradients are small, that's why the flow is treated as inviscid. And since the most of the flow field is inviscid, that's why it's better to have at least have an idea how the flow would have behaved if the flow was not viscous, right? So is it clear up to this point why to study Euler's equation?
Yes, sir, clear.
Okay,
Yes, sir.
thank you so much. So I guess discussion part is enough for this much enough. So, and regarding the derivations, I strictly suggest you to look at Professor Chakraborty's lectures. He has derived it very beautifully, so I guess you will understand more. And also I cannot discuss because I have to discuss the some questions also. So yeah, so I guess I will strictly directly go to the question and answers. So yeah, so okay, so let's discuss the questions. Okay, I'll dictate the question once, and this I could say that this week's questions are quite involving, so you need to solve it. Okay, you solve it by yourself, and then tell me the answer, and also you need to tell me how you have solved it, and then we'll compare. Okay. Okay. A steady two-dimensional inviscid flow field is represented by the stream function this, okay. Psi is equal to ax square y, where a is a non-dimensional constant. It's a constant, okay. It is known. Consider 2 points. P is 1 by 9, 1 9, and Q is 3 1. I guess it is Cartesian coordinate. I'm wrong. It's 2D, okay. In the flow field. So which among the following statements is or are correct? So you can see the options. So yeah, it might happen in you might have solved the question before, but still, if you tell the answer, you need to tell me the steps. How you at least tell me the steps how you have solved it, okay? So yeah, please read the question and just tell me what would be the correct answer. Psi is given and it's given that a is constant, so we need to find whether the flow is irrotational or rotational, or the boundary equation could be applied between the points P and Q. So all the assumptions that were considered, you need to cross verify them by mathematically doing that. So it may take some time, but still I encourage you to do that. We have, I guess, 1 hour, but I don't think we will need 1 hour, but still you can try. Yeah.
Hello, sir.
Yeah, please go ahead.
So the flow field is rotational,
Okay.
and it can be Bernoulli's equation can be used to evaluate the pressure difference.
Okay. Okay, let me stop. Like, okay, you can wait for a while. Let me see how Anurag and Abhishek has approached. So, but since both of you have not attended, completed this week's lectures, so it's fine if you're not able to solve them. Okay, but if you have solved them, you can tell me. So, what's the case? Are you solving it, or like, but you need to attend the lectures before solving them? Please be frank.
Sir, I need to attend the lecture, sir.
Okay, okay, sure, sure. I guess same case for Abhishek also. I don't know. Okay, it's fine. Okay then.
Yes, sir.
Yeah, sure, sure. Okay. Then I guess since Priyanka has attended the lectures, so okay, then we can just work it out. So she may suggest, and then we can see how they have approached. Okay. So yeah, Priyanka, please tell me how you have approached the question, like how you have obtained this. Okay, let me tell. These are right options. So B and C are correct. That's it. But how you approach the question? Could you please tell us?
So I found the um, u and v velocity
Okay.
from the stream function.
Okay. So you're telling. So how you find it? I don't know. Please tell me.
For u, it is dou psi by dou y.
And V equal to.
Minus dou psi by dou x.
Okay. So again, I'm 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 sorry that I was not sure whether it is in Cartesian or not. It is in Cartesian actually. So this okay. I'm just correcting myself. Okay. So you have found out U and V from Abhishek and Anurag. I suggest, even if you not attend the lectures, please follow the steps. It would be very helpful for you when you attend the lectures, and like just try to connect the concepts. Okay, you can just
Okay, sir.
be in the session. Okay, thank you. Okay, so you have found out U and V. Okay, so V, I guess you can write in the vector form as Ui cap plus Vj cap. Am I right? Yeah. Okay, and then to find the whether the flow is rotational or not, you have, I guess, evaluated del cross V, right?
Yes, sir.
Yeah,
Yes, sir.
yeah. Okay, so I guess she is right, and I also have followed a similar procedure. So just to be sure, so let me check. Okay, so uh, just to help Abhishek and Anurag, I'm showing the steps, because in general I don't show the steps because I encourage students to do themselves. But since both of you have not attended, so you can just see the steps. So Priyanka, if I'm wrong in any steps, you can just tell me. Okay. So Anurag and Abhishek, okay, for you only. See, they have mentioned the stream function psi. Then since the flow is steady and 2D, it in viscid flow field. Since 2D, we need only, actually stream function is only valid for 2D flows, but still we only need to find the u and v component. So we found out u and v component using these identities, and then after doing that we found out u and v respectively. And then to find whether flow is rotational or not, we find the del cross v, the curl of the velocity field. So after doing that, we found out that it is not equal to 0 because we obtain this 2ay is equal to 2ay k cap, del cross v equal to 2ay k cap. That's why the flow is rotational. So option B is correct. Flow is irrotational. Okay, so up to this point, I guess we did the same thing, right, Priyanka?
Yes, sir.
Okay, so again, can you tell me why you thought that how you obtained the second option? Like you can apply Bernoulli's equation between the 2 points. Could you please tell me?
Sir, applying the streamline equation, sir.
Okay,
I use dx by u is equal to dy by v option.
Okay,
Equation.
Okay, dx by u is equal to dy by v. So what did you get? Just tell me the final step, final answer, final equation. Some function of x and y equal to some constant, I guess, like that, right?
Yes, sir.
Okay, what was it? Could you please tell? So it will be helpful to them also.
I got ax square y.
X square y equal to some constant. Okay, so yeah, actually you have followed the right steps, and it is actually how you can approach the steps, because I've also approached the similar steps. You can see from the equation of streamline. Oh, sorry. From the equation of streamline itself, I try to solve it and get an equation. So I also got x square y equal to c. And after that, what did you do? Okay, no problem.
Sir, actually, I did a mistake, sir.
Okay, what happened?
I took that constant and zero automatically.
Okay, that's the we cannot take it 0, right? While integrating.
Yes.
Yeah. So no problem. So there would be a constant. It's very important. So there would be a constant. So, but still, how did you say that? Then again, then that it is C. If you have not got the constant, then how you have said this was the correct option?
Sir, actually, what I did was that minus, we get v minus, no, sir. I didn't consider the minus, so automatically it got cancelled and it came 0.
Okay.
So I thought, okay, satisfied the equation.
Okay. So you need to correct it. So actually, when you do that, you get the equation of this one. Okay, Abhishek and Anurag, if you have doubt in any point, you can just stop me. Okay, I will repeat it again. So you get the equation of this from x square y equal to c. I will tell you again a much okay. I will tell you again much simpler form without the need of solving this much. You can just write it, but let's go to the pain right now. So if you substitute the value of x, the coordinates in this equation, you'll find that you'll get the same value of the constant. Okay, you will get the value of cs 9 and 9 here as well. So keeping that in mind, since the constant value is the same, these 2 points lie on the same streamline. Okay, and since we have told that if you have been given the Bernoulli's equation and it's not mentioned that whether the flow is irrotational, sorry, if it is not mentioned that whether the flow is irrotational or not, then it is valid only along a streamline. But since you have already found out that the flow is rotational, then the Bernoulli's equation will be only valid for points that lie along the same streamline. And since these 2 points lie along the same streamline, this is also a correct solution. But again, there is again a shortcut, and actually I guess this should be the right approach. What you can do is you can directly substitute the value of these points in the stream function. Okay, so you will get the solution as uh, for P you will get 9a, then again for Q also you will get 9a. So say psi 1 and psi 2, just for saying, and since these two are same, you can say that they lie along the same straight line. Just it's shortcut. Okay, you can follow the same steps, just an additional constant you will get. So I guess it's clear up to this point. The first question is clear.
Sir, what was the special assumption of the Bernoulli's equation you mentioned at the starting?
Okay, the thing is that special assumption is that, like, usually there are four strict assumptions. That is, the flow is steady, in viscid, the density is constant, and the Bernoulli's equation would be valid along a streamline. That because we consider Bernoulli's equation for 2 points, right? So what we do is these 2 points should lie along the same streamline. But if the flow is irrotational, that the curl of the velocity field, that is del cross v is equal to 0, then we can say that the Bernoulli's equation will be valid for any 2 points between the flow field. So if the flow would have been irrotational, then there's no need of checking whether they lie along the same streamline or not. You can directly say, yeah, the Bernoulli's equation is valid for the points P and Q, whatever they may be, because the flow is irrotational. But since the flow is rotational now, you need to check whether the points P and Q lie along the same streamline or not. And since we have found out that they lie along the same streamline, we can say that the Bernoulli's equation can be used to evaluate the pressure difference between the 2 points P and Q. I guess that was clear. So
Yes, sir.
okay, thank you. So yeah, so we look into the second question, and again it's a common data type question. So okay, let's look at the question. Okay, a heated rectangular electronic chip floats on the top of a layer of air thin layer of air above a bottom plate as shown in the figure. Okay, I should not do it. Yeah. Air is blown at the uniform velocity v0 through the holes in the bottom plate. The width of the chip perpendicular to the plane of the figure is L. So basically the mean is that if it is along the Z direction, then this is the plate is having a chip is having a length L outside of this sheet. So assume a steady, inviscid and constant density flow in the gap between the chip and the bottom plate. So I guess you're getting it. They're strictly mentioning the assumptions of the Bernoulli's equation. So yeah. So given these assumptions and this diagram, I insist you to draw the diagram first, like just a rough diagram, so that we can look into the question. So is the question clear? Just read it. I guess it's clear. A chip is floating over a bottom plate through which a fluid is flowing through the pores. I guess, yeah, through the holes from the bottom plate. So air is flowing through the holes, which is balancing the weight of this chip. Okay, this is the question, or they're describing the question right now. They're building up the question. So this is how they have described the question. So is it clear? Because I need to scroll down to look in the next to the question. Okay, I hope you have drawn the diagram, and they have mentioned dimensions. So initially it is floating at a height of h from the surface of the plate, this bottom plate, and it has a length of b. So they have asked the question that the velocity field in the gap between the chip and the bottom plate is given by, they have given these four options. So you need to find the velocity field, basically u and the v component of velocity within this gap. Okay, so I hope it is clear. You need to find u and v. So please go ahead, at least try. I think this may be a bit difficult because you need to apply a lot of concept together, and it is the, what to say, the gist of the course, that as we go deeper into the course, you need to pile up all the concepts together and apply it to the concerned problems. You just cannot forget the previous concepts, you need to apply them also. So yeah, please try. You may take some time, I'll be here, so you can try. Sorry again. So,
Hello, sir.
yeah, yeah, please go ahead. Yeah. Okay, let me go to the options. Yeah.
So U is,
Okay, u is equal to
sir, option B.
b. Okay, okay. U is
B, sir, B, B.
b. B. Okay, okay.
D.
I'm sorry, D or B? This one, right? I'm
Second one, sir.
this one, right?
Yes,
Okay, okay,
sir.
okay, okay. Sure.
Yes,
Sorry,
sir.
I'm sorry. I'm having slight difficulty in hearing. That's why I'm asking. Sorry. So you're saying it is v naught x. Sorry again. V naught x by h, and v is equal to minus v naught y by h. Okay. Again, we go through again. So how did you find it? Let me go back to the diagram. I was just drawing. I was trying to visualize the flow field myself, but I think it is not right. But still, you
Uh,
can tell me. Yeah, please go ahead.
Sir, use the equation of continuity, sir.
Okay, tell me. I don't know.
Uh,
Please.
I took a small section.
Okay. Say okay. I will draw it.
I took a small rectangular section.
Okay, okay. I'm trying to draw it because I think you have taken something like that because it would only make sense. Is that so? Or
Yes, sir.
it extends up to here? What do you say? Okay,
Sir, extend.
this one, right? Okay, right. Actually,
Yes, sir.
okay, okay. And then, so what would be inlet?
The inlet will be V naught
Okay, let me write the. Tell me the.
V naught into
No, no,
X into L.
no. Tell me the. Okay.
V
Just
naught into X
no, no,
into
no.
L, sir.
Wait. Just out of concern, okay. I feel like you're having some cold, so Is it very difficult for you to speak up? Like, I don't want to pressurize your throat if you're having cold. Like, you can speak up a little bit also, just fine. Tell me fine.
Yes, sir. Slight cold is there,
Okay,
sir.
okay, I understand. Okay, so yeah, that's fine. Okay, so let me go ahead with the answers. We understand. So that's fine. Okay, no problem. I will write my solutions myself. So if you get something correct, or like you feel that, oh, this is what I should have done, or no, you're doing it wrong, just kindly point me out. Okay. Okay. So I already did it. So yeah. So here what I have done is, I have drawn a diagram, and my apologies that I have drawn the control volume in a wrong fashion. She was right. I should extend it up to here. So the control volume should extend up to the exit for accuracy. So it should be here, but I guess you understand that it gives the same idea. So this is the chip, it is floating. So this is the inlet velocity, and they've mentioned it strictly that it is equal to v naught. Okay, so here I is the inlet and E is the exit. Okay, so basically the flow comes through here, strikes the plate. Since it has does not have anywhere else to go, it exits through here. Okay, and the same flow is symmetrical, so it will follow the same fashion. It will go strike it and go here. Okay, I'm just doing the half of the flow field because it is symmetrical. There's no point of solving the entire geometry. It will be symmetrical here also. So I guess it's clear up to here. So, and the coordinate system that chosen is, this is the y direction and this is the x direction. So I guess it's clear up to now. And this is the h, the height up to which the chip is floating. Okay. So, and then we need to find out the u and the v velocity component, and in the second part of the question you need to find the acceleration also. So yeah, so since the flow is steady, constant density, then the continuity equation takes this form. Okay, because essentially the time derivative term will get cancelled out because the flow is steady. Not cancel out, it will get omitted because the flow is steady. So that will equal to 0. So we only deal with the inlet and the outlet, what to say, mass flux. So ai ui equal to ae ue. So ai is the inlet area, ui is the inlet velocity, ae is the exit area, u is the exit velocity. So the inlet area I have taken as L into X, because say this is the length X. Okay, I have not taken it directly as B by 2 because uh okay, with this assumption, I guess, with this control volume, I guess for my assumption it was okay because of how I considered it. This is right, so I have to take up to X. Okay, I have not taken up to B by 2. So for this control volume, my inlet area will be L into X. L is the 3D, what to say, the outward length, and X is the this length. Okay, so this is the inlet area, and similarly what would be the outer area? Outer area would be L into H, I guess. Not I guess, it is L into H. So this height and depth L. Okay, it is L into H. That only written this AI, this is A. Then it is v, the inlet velocity is constant, which is equal to v naught, and the outlet velocity we don't know. And since the flow is inviscid, we can assume that it does not have any viscous effect, so the velocity will be constant throughout the height. Okay, this is, we can only say it to be constant when the flow is inviscid, because of otherwise it would have some boundary layer effects, because we have discussed it right just before approaching the question answers, right? We have considered about, we have discussed the boundary effect and how it affects the velocity profile. So since the flow is inviscid, we can assume that the velocity profile at the exit will also be uniform throughout the length. Like it would not vary along y. It may vary along x, but it would not vary along y. Is this concept clear? Yes or no?
Yes, sir.
Yeah, thank you. And that's why we have taken it only as a function of x. Okay, so you can get the uvx would be equal to v naught x by h. I guess this is clear up to this point. And again, to find out the v component of velocity, we again take the help of the continuity equation. So where you get that del u by del x plus del v by del y would be equal to 0. I'm sorry, okay, this is not the continuity equation, this is actually the, sorry, you should have corrected me, this is actually the mass conservation. So yeah, the entire mass conservation form, like not the we simplify it to obtain a continuity equation, but this is the entire mass conservation equation. And then by applying the continuity equation, we get that del u by del x plus del u by del y equal to 0. How we get it? Because rho is constant, so rho cancels out, and all del rho by del x term, del rho by del y terms cancel out because rho is constant. And again, the steady part is, because unsteady part is 0, so we reach this equation, del u by del x plus del u by del y equal to 0. And what we get it is, so what would be, since u, I should write it, I guess it is very unclear now, I guess, since u is equal to v naught x by h, we substitute it here, so del u by del x would be equal to v naught by h, right? So we get v naught by h and plus del u by del y equal to 0, and del v by del y equal to minus v naught by h. So when we integrate it, we get minus v naught y by h plus some function of x. Why? Because this is partial derivative, right? So we cannot directly say that it would be a constant, but it can also be a function of x. Is that clear?
Yes, sir.
Yeah. So it would be some
Yes, sir.
it would be some function of x. So then we apply the boundary conditions. So I guess here we only know one boundary condition. We also, one of the boundary conditions would be this, that at y equal to h, v equal to 0. It is basically that when y is equal to h, v would be equal to 0. Why? What is this boundary condition known as?
So the velocity cannot pass through the chip.
Yeah, exactly. So this is known as the no penetration boundary condition. So keeping that boundary condition in mind, we get that f of x would be equal to v naught, and we substitute this here, here, to get v is equal to v naught 1 minus y by h. Okay, so we get the velocity fields from mass conservation and the continuity equation. Okay, so I guess it's clear up to this point. So when we look at the options, so I guess option D would be correct, right? And I feel,
Yes,
I feel Priyanka has
Yes, sir.
missed the f of x part, the partial derivative part.
Yes, sir.
Yeah, that's why. So keeping that in mind, we get u and v as this. So now they've asked us to find the acceleration of the fluid particle in the gap between the chip and the bottom plate. So it's very easy. You know u and v, so you need to find ax and ay. So yeah, Priyanka, I can say that you can try and just tell me the answer. You don't need to explain. Like you can, when I ask you can say, but for now you can just tell me the answer after you have solved it. And I guess Anurag Abhishek has left. Anurag can also try, since you know how to obtain the acceleration of a flow field when you know the velocity components, right? So you can also give it a try.
Yes, sir.
Yeah. Very simple. It's only calculation. There is no other concepts.
C.
C. Okay. We'll wait for Priyanka also. Let her finish. Okay, I did it wrong here.
Yes.
Yes. Okay. So I don't think I need to explain, because both of you have told the correct answer only. So it is indeed option C. So thank you. Yeah. So this is, I guess, difficult.
Sir, C.
C. Yes.
Hello?
Yeah. Is it wrong?
Sir, sir, it should be v naught square by h square, no, sir?
Okay, let me check. Mm, is it? Anurag, can you please verify? Should it be V naught square by H square?
No, sir. It's got sorry, sir. Sorry, sir.
Oh, I guess
Sorry, sir.
we
Sorry,
take
sir.
common. So yeah, I guess yeah.
Sorry, sir. It is correct.
Okay. Thank you, both of you. Yeah. So let's look at the next question. Yeah, I feel this question is the most difficult for this section, I guess. You need to find the weight of the chip that can be held in equilibrium by the injected air. So let me go back to the question, okay, to clarify. So what was happening is that we are blowing air from this bottom surface in the upward direction, and what would happen? See, there is a plate, so it would have some weight, right? It would have its own weight, so it will try to fall down. But since we are injecting air from below through this porous medium, I can say, this is what that's pushing the plate, that's preventing it from falling down. I guess you get it, right? it's it's just like some anti-gravity chambers, right? When you what that you see in some science documentaries, like people how they encounter anti-gravity all by being in earth also, like just their mass is balanced by the injected air from the below below from below they inject air at very high mass flow rate, so that their mass is balanced. So there it is mentioned in the question that it is in equilibrium, okay? The body is not falling, it is at a constant state. The weight is exactly balanced by the mass flow rate, so this mass is not moving at all, it is at a constant state. So keeping that in mind, you are asked to find the weight of the chip. Okay, this is a bit tricky question, and actually sir has Professor Chakraborty has discussed similar example in the lectures. So if you remember that, you will be able to solve it. But if you cannot, that's also fine, because it's a bit tricky part. So I insist you to try. Anurag, since you've not attended, it's fine. But Priyanka, like if you've attended, you can give it a try. So just as a help, I would encourage you to draw the free body diagram of the present case. Like, you can draw the free body diagram. That would be very helpful. Okay, welcome, Venkatarami. Welcome. So, uh, since you've joined a bit late, So we have been discussing about the week 7 of the Introduction of Fluid Mechanics course. We have discussed the Euler's equation and the Bernoulli's equation, and now we are trying to solve some questions regarding uh, the week 7 concepts. There is Euler's equation and Bernoulli's equation. So okay, am I audible, Venkatarami? Okay. So just to give, yes, sir. Okay, thank you. So just to give an idea, what we are dealing is that we are considering this question. So where there is a chip that is floating in the air because of an influx of air from the bottom surface, as it is drawn in the diagram. So because of this flow of air, it is balancing the weight of this chip that they're mentioning. So keeping this question in mind and the given geometry and the given specifications, the third question of this big question, the third sub question of this question asks us to find the weight of the chip given that the chip is in equilibrium. So you can give it a try, that's fine. If not, like, don't also it's fine, because again it's a bit difficult for me to repeat again. But if you want, you can give it a try. Others are also trying, so we can just compare, like, what is right or wrong. So yeah, you can give it a try, or else just you can be here so you can see how to approach it. Yeah, is that fine? Okay. So yes, Priyanka.
So second option.
Second option.
Yes, sir.
Okay. The thing is that I'm it's correct. That's why I'm very happy. It's correct. So it will be very good. Like if you're feeling a bit fine, you can just tell me the few steps or just the formula. Okay, let's draw a free body diagram. Could you help me, like, how to draw the free body diagram? Say this is the chip. So what are the forces acting here? Yeah, please help me out. That would be helpful. Yeah.
Sir, there will be pressure from bottom.
Okay.
Weight.
Wait. Let me draw. Pressure from bottom. So P. So there would be weight and something else.
Atmospheric pressure.
Yeah, this is very important, and it's very essential because I also ignored it while solving it first. But after visiting Professor Chakraborty's lecture, I got like what I was doing mistake. So it's very important. Okay. So after that, given this free body diagram, now you know. So could you just tell me uh, steps? Just tell me the important steps. That's fine. I don't need to tell a detail. I already have the solution, but tell me the steps. How you solved it first.
Sir, applying the Euler's equation.
Okay, you applied Euler's equation to get what?
To get the pressure equation.
Yeah, great. To get the equation for pressure, because you need to get P, right? Pressure equation. Great. And then how did you what was the expression for pressure? Can you tell me that? That would be helpful. P is equal to PA plus
rho V naught square by H square bracket B square by 8 minus X square by 2.
Yeah, I guess this is it. So did you apply any okay, that's fine. Thank you. And what was the final expression that you used to find weight? You can tell the formula. Weight. From the free body diagram, how did you find the weight? Given you know P now.
P minus PA.
Yeah, but again, P, you don't know P for the entire surface, right? You know it is a function of X. So tell me the entire formula, because here P is what? P is P of X, right? So you cannot tell weight is equal to P of X minus PA, right? That doesn't make any sense.
I integrated it, sir.
Yeah, tell me that. What was the expression? Integration, tell me the expression that you integrated.
I took
From limits, tell me the limits.
uh, due to symmetry, I took 0 to B by 2.
Okay, then is there a 2 here?
Yes, sir, multiplied by 2.
Okay, then P minus PA dx, and there will be some
NTL.
L. Yeah, thank you. So yeah, absolutely correct. So I guess this is fine up to now. So yeah, so I guess Anurag and Venkatrami can check the steps. So what you should do is first draw the free body diagram. Okay, this is very essential. Draw the free body diagram. Then to know like what other things I need to find. PA is a constant that you can deal with because there's no additional requirement for that. You can just treat it as a constant. W is what you need to find, and P also you need to find at least the expression, the functional form of P, so that you can mathematically play with it. Otherwise, like this is not or at least this is not one of the options here, so you cannot say directly like this. So you need to have some mathematical form so that we can integrate, differentiate, whatever you want to do. So what you do next is that you apply the Euler's equation. Why Euler's equation? Because the flow is inviscid. They strictly mentioned it. So you can apply Euler's equation. Then using Euler's equation, you get the equation for pressure. Basically, you get the expression for the pressure gradient del P by del X, if I'm not wrong. And then if I integrate it for certain limits, uh, okay, let me ask you, what was the boundary condition that you used to find the integration constant? Priyanka, could you please tell? Boundary condition, because I guess there was some integration constant. Yeah.
Sir, I took at the end, it is atmospheric pressure at X equal to P by 2.
It is, yeah, that's why. Sorry. P, right. Okay. So P equal to P. Yeah. So using this boundary condition, you find the integration constant to find the expression for P. So then after obtaining that the expression for P, then you again go back to your free body diagram, obtain then you, since you know the pressure is a function of X, then you need to apply the balance that P minus PA would be equal to W. That's right, but it is a function of X, so you need to integrate it along the X direction. So you integrate it, and since the flow is symmetrical along the, if this is the along the y axis, so you can integrate it like 2 equal to b by 2 0, or from 0 to b by 2, or else if you want to avoid the 2, you can just take it as minus b by 2 to b by 2, because you have taken the coordinate system like this, right? Sorry, you have taken the coordinate system like this, and that's why origin lies here, not here. So it will be minus b by 2 to b by 2. So keeping that in mind, then after you integrate it, you get the solution like this. So I just told the steps that I can, so that I could show you the solution. So yeah, similar to that, yeah. We draw a free body diagram. From the Euler's equation, you get the expression for pressure. Then you know Ax from the previous solution, also you get the expression for Ax. Substitute Ax here. Then you get the equation for del P by del X equal to some rho, all known terms and one variable, that is the independent variable, that is x. So we integrate it along x at y equal to h. This is also important. You need to find the pressure acting here, right, at y equal to h. So integrating that, you get P is equal to this some term with some integration constant, right? and then we need some boundary condition, one boundary condition to get the value of C1. So as Priyanka has rightly pointed out, at x equal to b by 2, p equal to p, right? From the geometry itself you can understand, sorry, yeah, because here the pressure would be the atmospheric pressure, right? It is p equal to pa. So keep with that boundary condition, we get the expression for p, which is a function of x. Okay, so again applying the what to say, the for the free body diagram, balancing the forces, you get this expression for W. Weight is equal to 2 uh, 2L integration 0 to b by 2 rho v naught square by 2h square b square by 4 minus x square dx. So you integrate it, okay, for equilibrium condition. So you integrate it to get the final expression like this. So I guess the steps are clear, because I'm not doing it hand by hand, because like the steps that you need to follow are more important than the solution itself. So I guess the steps were clear. Okay, Anurag and Venkat Rami, I guess the steps were clear. Okay, thank you. Okay, so we can, I guess we are short of time now, but not, we have some time to deal with the next question also. So okay, so this is the second question, third question for today's session. That is, a tornado may be modeled as a combination of vortices with Vr and Vz equal to 0 and V theta is equal to V theta of R. Then V theta is a function of R, such that V theta is equal to omega R for R less than R. Like if you treat as it is a circle and this is R, then for the inner region at R less than R, you can say the velocity field V theta is given by omega R, where omega is the angular velocity, and V theta, which is constant because they've not mentioned it, so this is constant, you can take it as a constant for now, and V theta is omega R square by R for any region outside the radius of the tornado. Is it clear up to this point? Vr Vz is equal to 0. It's very simplified form now, and only there's one velocity component where which is a function of R, the radius of the tornado. Okay, I guess I should draw it, it would make a better sense. So if this is the tornado, this is the radius. So for in this region V theta is equal to omega R, and in this region V theta is equal to omega R square by R, and take omega is equal to constant for all the calculations. Okay, assume the flow to be inviscid and the fluid density to be constant. Also neglect the effect of body force due to gravity, and also assume P tends to P infinity as R tends to infinity. Okay, and this is a diagram. Okay, so before going any further, could you, any one of you please tell me what is the coordinate system that they're using here? Coordinate system.
Polar.
Okay, polar also there are two, right? So which one? R theta z, which coordinate system? It's fine, at least you told polar, that is very good. So this is would be cylindrical. Okay, cylindrical is R theta and z, and spherical, what would that be? Any one of you?
R theta phi.
Yeah, thank you. And just for conceptual, in Cartesian would be XYZ. Thank you. And since we are dealing with R, Z and theta, you should directly get the idea that they are now dealing with cylindrical coordinate system. There is no use of equations in the Cartesian form. So now you need to think, or at least go through back your notes and see what were the governing equations in the cylindrical coordinate system. So you can go through that. But let's see what the first question they've asked. I guess the question is clear. They've told that V theta is different for the inner region of tornado and the outer region of tornado. Okay, V theta varies. So the first question they've asked is that question number 5. Which among the following statements about this flow field is true? Okay, so you can check the options. Okay, I can draw it. I should write it so it will be easy. It is omega r for r less than r, and omega r square by r for r greater than equal to r. Okay, so given this velocity field, you should check which of the following options are correct. Okay, so yeah, I guess we are short. We have only 15 minutes left for today's session, so I would insist you to go a bit fast. So I'll give you very less time for each question. Sorry for that, but still, uh, you can try. Give you 3 minutes for question number 5. So please go ahead and at least try. Then let's see what happens.
Sir, option C for fifth one.
C. Okay, let me check. The flow field is rotational in the inner region but irrotational in the outer region. So okay, you have solved it, but let me ask Anurag. So could you please tell what did she actually do here to get the option, to get the correct option? What we need to do actually? Checking the curl of. Yeah, absolutely correct. Yes. So you just need to find the curl of the velocity field, which is only the one single component v theta. You need to find del cross v for both the inner region and outer region. So what was for the inner region, Priyanka? What was value of del cross v?
Sir, actually, I didn't find the curl.
Okay.
It looked like the equation of free and forced vortex.
Yeah.
So
Yeah.
said the option C.
Yeah, absolutely correct. Absolutely correct. So it is actually tornado are indeed modeled by the combination of free and forced vortex. So since the inner region is a forced vortex, if I'm not wrong, right? The inner region is acts as a forced vortex, right?
Yes, sir.
Yes. So the flow is rotational, and it will actually turn when you find out the curl of velocity field, it will turn out to be 2 omega, and for outer region it would be equal to 0. So right, let me use the terms also. Forced vortex. Okay. Okay, thank you. So keeping that in mind, and even if you don't know the concept, you can just directly find the curl of the velocity field, and you can see that the inner region is rotational and the outer region is irrotational. So yeah, thank you. So I'll go a bit fast because we are short of time again. Consider 2 points A. Again, they have used the r and theta coordinate system. So r is 3r by 2 and theta is pi by 6. Then B is r is a 2r, theta is pi by 3. In the flow field, identify the correct pair of statements. So yeah, again, please go to the statements and tell me which is the correct one.
So since it is beyond R and it is irrotational, can we say that we can apply Bernoulli's equation?
Yeah, but can you are saying that the Bernoulli equation can be applied between the points A and B and calculate the position. Okay, so 3 is correct. So what is the correct option? There are pairs of solution, right? The 3 is in both A and D. So which is correct, A or D?
Yet to find out, sir,
Yeah,
regarding
yeah,
first and second.
you need to find out. Okay, so since I would say the time is short, so if you don't mind, like I would just like to tell the answer so that I can cover up the uh, entire questions. So is that fine?
Yes, sir.
Okay. I'm really sorry, but like since the time is short, so I would like to tell the answer. Not tell the answer directly, but insist you to try. So what you need to do is you need to find the equation of the streamline for this case, right? So and since you can see that 3r by 2 and 2r is greater than both 3r by 2 and 2r is greater than r, so the flow is predominantly irrotational and the velocity field for this case is given by v theta would be equal to omega r square by r, right? So then let me check. I also forgot the equation, I'm sorry, but I've solved it. So okay, yeah, so for this case the equation, the relation between uh, the velocity components in the stream function for a cylindrical coordinate system is given by this expression. Okay, ur is equal to 1 by r del psi by del theta and u theta is equal to minus del psi by del r. And since ur is equal to 0, we don't need to deal with the r coordinate system, so it's completely fine. So we can directly say that del psi by del r is equal to minus omega r square by r, right? Minus omega square by r, keeping this equation from this equation and integrate it, since psi is only function of r because it is not a function of theta, right? You will get it from the continuity equation. So you can say that del psi is c del r by del r. When you integrate it, you get psi is equal to c natural log of r plus some constant. And here you can directly see that psi varies with r, right? And does not depend on theta at all. Is it clear that psi is c l, sorry, I should write it, I guess, that psi is equal to c l and r and plus c1, which is an arbitrary constant. So here you can see that psi depends only on the radius of the tornado. Okay, so and since in this question 3r by 2 and r2 are not equal, so this imply two different streamlines. Okay, these radii, two different radii imply two different streamlines, and that's why you can say that these 2 points do not lie, sorry, do not lie on the same streamline, that this point B does not lie on a streamline passing through point A, and that's why the correct option would be D, 2 and 3. Okay, but again, since the flow is irrotational, you can apply Bernoulli's equation in any 2 points in the flow field. So you can apply Bernoulli's equation at point A and point B, but these 2 points do not lie on the same streamline since it depends on radius. Okay, if these two would have been same, then you could have said that point B lies on the same streamline passing through point A. Is that clear?
Yes, sir. Yes, sir.
Thank you. So yeah, so let's take the last two questions. Again, I'm very short of time. So yeah, assertion A. So this is assertion and reasoning type question. So this is question number 8, I guess. The lowest pressure in the flow field occurs at R equal to R. Okay, this is they're asserting. Reason is that since the Bernoulli's equation can be applied between any 2 points in the flow field, P plus half rho infinity square is a constant throughout, constant throughout. Therefore, pressure will be minimum at the location where the velocity is maximum, that is at R equal to R. So, which of the following statements is correct? Options are correct. Sorry.
So we can say R is false.
Yeah, but again, there are two options, C and E. So which is correct. R is false, absolutely, because we have, it is given in the question that the flow is not irrotational throughout. So we cannot apply boundary equation between any random 2 points within the flow field. So that is correct. But again, you need to say whether A is true or not. Is the lowest pressure of the flow field located at R equal to R? Is it so? Okay, I'll give you 2 more minutes, then I will just have to go fast because of time constraint, but still you can have 2 minutes and just think of it. Like, it is indeed a lengthy problem because you need to solve the Euler's equation and find the pressure field for the entire flow field, and you know that it would not be the same for two cases because one is rotational, other is irrotational. So the pressure field will be different for, I'm sorry, yeah, it would be different for the two different regions, and you need to find the pressure field separately and then reason with reason with the given statement, like whether it is correct or not. So I guess since we are short of time, like if you all don't mind, I will just show you the solution, how we solved it, and you can just try later. Okay, the gist is that you need to find the pressure field. Find the pressure field for R less than R and R greater than R. You need to find the pressure field. Sorry. Okay, so is that fine if I show the solution? So
Yes, sir.
okay, I'm very sorry. Okay, you're short of time, so that's fine. So we need to find the pressure field, right? And so we again apply the Euler's equation. So along the R direction, because you will eventually see that all the other terms along that is the Euler's equation along the theta and the z coordinate gives you 0 because the velocity field is 0. So eventually all terms with 0 will be equal to 0, and you will find that p will only be a function of R. So actually I should have written like del p by del R is equal to rho v theta square by R, because you will from the from the theta and the z coordinate system you will get that del p by del theta is equal to 0 and del p by del R equal to 0. So this is basically imply that p is only a function of R. Okay, so keeping that in mind, we integrate the equation respect to R, then we get that p is equal to rho v theta square by R dr plus some integration constant. Okay, then now first we solve for the outer region. For the outer region, what we do, we substitute the value of v theta in this equation, that is omega r square by R. Then we integrate it. Then after integration, we get this equation. Okay, then we need to find the arbitrary constant, right? So to find the arbitrary constant, we use the boundary condition that I have mentioned, that p tends to p infinity and R tends to infinity, where you see they have strictly mentioned here, right? So use this condition to find the arbitrary constant. Okay, so using that constant, we find that C1 is equal to P infinity. So we get the pressure field for the outer region as P equal to P infinity minus rho omega square R to the power 4 by 2R square. And again, since the velocity field is different for the inner and outer region, we need to find the pressure field at the inner region. So again, I am again sorry, this should be the inner region. Yes, for inner region, then again we substitute the value of v theta in this equation. Then solving it, we find the expression as p minus rho omega square R square by 2 is equal to C1. Then again we need to find the value of C1. But here thing is that if we use a similar boundary condition, that P tends to P infinity as R tends to infinity, what do you think the problem would be?
We will get the infinity term, so
Yeah, this will
in the constant.
this term will go to infinity, so we cannot use that condition. Okay, so what we do is that we suppose, or like we, what to say, I can say we assume a condition, let P equal to P naught at R equal to R. Okay, say, because see, similar to Bernoulli equation, if P minus rho omega square R square is equal to is a constant, then P1 minus rho omega square R1 by 2 is equal to P2 by rho omega square R2 square by 2. Is this correct? Like, I have just used the concept from the Bernoulli equation. Okay, so we say that at P equal to P naught, sorry, let P equal to P naught at R equal to R. We don't know what is the pressure at the radius of the tornado. Okay, so we assume that it is equal to P naught. So keeping that in mind, we substitute this condition at the right hand side to get that P minus rho omega square R square by 2 is equal to P naught minus rho omega square capital R square by 2. So is this step clear? How we obtain this, we obtain this from equation 2. Yes or no?
Yes, sir. Yes, sir.
Okay, thank you. So again, so what we just what to say, play with the terms to get equation 3. Okay, P minus P naught is equal to rho omega square R square minus R square. So we get equation number 3. Okay, then what we do is, from equation 1, this was the equation. Again, we have assumed that let P equal to P naught and R equal to R. How we could assume? Because see, the at the tornado, the point R, that is R equal to R, is valid for both the inner and the outer region. Okay, so is a boundary condition for both the inner and the outer region. So for the outer region, the pressure field in the outer region, we assume a condition that P equal to P naught and R equal to R. Okay, that is what we have considered, right? So we are now approaching this boundary from the outer region. Okay, so we are writing P equal to P naught and R equal to R. We don't know what is the value of P naught. Okay, we are just finding out with respect to the radius of the, with respect to some known terms that we know from the equation. So we find that P naught is equal to P infinity minus rho omega square R square by 2. Right, we just substitute R equal to R in this equation. Is that clear? We substitute R is equal to capital R in this equation to get, then this will become P naught. So we get this equation number 4. Is that clear?
Yes, sir.
Okay, so now what we do is, since we know the functional form of P naught in terms of the known values, known constant values, P infinity is constant, omega is constant that we took, R is constant, is the radius of the tornado, because they are mentioned as constant in the question. So since we know the value of P naught in terms of all the constants in the given case, what we do is we substitute equation 4 in equation number 3. Okay, we substitute the value of P naught, this value of P naught in this equation. Okay, I am scrolling too fast, I'm sorry. So we substitute the value of P naught here in this equation. Okay, so after doing that, what we find is that we reach we just substitute this and we obtain this equation. Okay, we get P minus P infinity is equal to rho omega square by 2 R square minus 2R square. And indeed, this is the next question that has been asked. Find the pressure field in the inner region. Okay, in the inner region. So answer C is the correct option. Option C is the correct option. So have I missed that? Okay, yes, but we still don't know the solution to question number 7. Okay, or question number 8, we don't know, right? We don't know the solution to question number 7. Sorry, we don't know whether the pressure is lowest at R equal to R or not. Okay, so we get this equation. So now what we do, since we know the expression, we again write p equal to, we just take it this term, sorry, take this term to right hand side, we get p equal to p infinity plus rho omega square r square minus 2r square. So by the concept of derivative, if you recall, I'm sorry, if you recall, you know that if the derivative of this del p by del r, because r is a independent variable in this case, the if del p by del r, I'm sorry, actually that it is with respect to r that we need to find where the lowest pressure lies, right? So we take the independent variable as r in this case. So if the first derivative of this is equal to 0 and the second derivative is positive, what would it be? What would it indicate? The minimum pressure or the maximum pressure? If the second derivative is positive.
Minimum.
Yeah. So keeping that in mind, if the second derivative is positive, you will find out that it will actually be positive, because see, 2r will become, first derivative will become 2r, the second derivative will become some positive constant value, right? Because rho is positive, omega square is positive, so it will get a positive value. So when we take the first derivative, we find that del p by del r is equal to rho omega square r, right? If you take the first derivative, this would be equal to 0, this would be equal to 0, so it will become rho omega square r. Am I right?
Yes, sir.
Yes. So when we equate it to 0, so we find that r equal to 0 for p equal to minimum pressure, right? Okay, just for clarity, del square p by del r square would be equal to rho omega square, which is greater than 0. So at r equal to 0, we will get p equal to minimum pressure, right?
Yes, sir.
So what would it mean? That it is wrong. So the correct option is option E. Both A and R are false. Okay. So question number 8 we have already solved before solving question number 7, because we obtained the pressure field in the inner region. So the final question that I have asked is, what would be the lowest pressure in this flow field? So we know that the lowest pressure is at r equal to 0. So just we substitute r equal to 0 at the inner pressure field to obtain that p equal to p infinity minus rho omega square r square, right? Because if we substitute r equal to 0 here, 2 and 2 will get cancelled out, so we'll get p infinity minus rho omega square r square. So keep finding that option, we get that this is the correct option. So is that fine?
Yes, sir.
Okay, so I guess this is all for today. Thank you. We overshoot the time limit. I'm really sorry for that, but I hope it was helpful. So again, let's meet in the next this next session. So I again insist you to watch the lectures of Professor Chakraborty very carefully, because I also sometimes miss some points or say something wrong. Then you can correct me if you watch the lectures carefully. So I insist you to do that. And so thank you. Yeah.
Thank you, sir.
Okay. Thank you. Yeah. Okay.